Hey there. I want to talk about snow. It snows a lot in Wisconsin, right? Like, it snows in October, it snows in November, it snows, like, basically all the time in Wisconsin. It's one of the reasons that I live here. I happen to love snow and ice and melting water and freezing water and the sound that it makes when it forms and the dead quiet of winter. Oh, snow. So, I want to talk about snow in relationship to calculus, where I want to remind you what's calculus again. Calculus is the language of change. Calculus is the language of change. It attempts to quantify change. And calculus breaks, broadly speaking, into two main domains, derivatives, or the so-called differential calculus, and the integral, or the so-called integral calculus. Okay? Derivatives let us answer the question, how fast is f? How fast is f changing? How fast is f changing? Whatever f happens to be, right? F is just some function. The integral asks the question, how much total change happened according to f? F plays a really different role in each of these two scenarios. How fast is f changing? How much total change happened according to f? Those are two sides of the same coin. They're just opposites of each other. And I wanted to talk about the derivative and the integral in terms of snowfall because, hey, it's Wisconsin and we get a lot of snow here. So, snow. What's the easiest way to measure snow in the world of change? Is it easier to measure how fast the snow is falling? Is it easier to? And I want you to think about this question here as we do this. Is it easier to measure A, how fast the snow is falling, or B, how much snow has fallen? Think about the answer to that question. Which one is easier? Which one is easier? Let's see here. So if I try to measure how fast the snow is falling, then I have to be able to measure like individual snowflakes. Like, that seems really hard to me. But I think it's a lot easier to measure how much snow has fallen because at the start of the snowstorm, I put a yardstick into the ground. And then I can just look at the yardstick and I know how much snow has fallen, right? So I think that the answer is B. It's easier to measure how much snow has fallen because I can just use a yardstick. Just use a yardstick. Okay, so we're gonna let that be. We're gonna let that be our function f. Okay, we're gonna let that be our function f. So we're gonna measure how much snow has fallen so far in this snowstorm. Because all we have to do is go outside and look at a yardstick. That is really, really super easy. Hey, and you even get it's a low-tech solution, and you get 2 units of measure at once, because you can use a 2-sided yardstick, one that has meters and one that has inches or feet on the other side. Okay, so what we're going to do is we're going to let our function f be the thing that was easier to measure. We're going to let our function f be the thing that's easier to measure. So f is going to indicate how much snow has fallen. That's our function f. And it's a function of time. So f is a function of time, so f of t. So we'll make that time dependence be explicit. Measures how much snow has fallen. Okay. So now I want to know how fast is the snow falling? Are we getting an inch an hour? You know, we're getting like 3 inches an hour, and it's like a crazy crazy snowstorm. Am I getting like 1/4 of an inch an hour? Okay. So how do I measure the rate of snowfall? So now I want the rate of snowfall. That's the derivative of f. The derivative of f is the rate of snowfall. And it kind of doesn't matter, but it kind of does. It kind of doesn't matter like what units. It's going to be like like feet or inches per hour. Which seems reasonable. Inches per hour. And the derivative asks how fast f is changing. F is how much snow has fallen. The derivative, how fast is f changing? How fast is the amount of snow that has fallen changing? Is the rate of snowfall. So this is df dt, the derivative of f df dt. As a practical matter, I'm going to look at my yardstick. Here's my snow. I don't have white. Here's my snow, and I've got a yardstick. It's marked. Okay? And this is what I can look at. So this is where I'm at, say at T1, and then I have this much snow at T2. Okay? So this distance right here is what we're going to call delta F. That's the change in F, the change in the amount of snowfall that has fallen. And the difference between T2 and T1, that's my delta T, the change in time. So inches per hour, delta F. Let's say this is, how many inches is this? These are inches. So it's going to be 1, 2, 3. This is 4 inches. We've got 4 inches of change. And let's say that 4 inches happened in 2.5 hours, 2.5 hours. Then over that time period, we would say that we did 4 inches in 2.5 hours. So what was the rate of snowfall in that 2.5 hour period? Is 4 over 2.5. 4 over 2.5 is 5/2, which is 2/5 times 4 is 8/5, is 1.2 inches per hour for that 2.5 hours. Right? 1.2. No, that 1.2 wasn't right. That's 1. I was doing a quick check. I wasn't like 1.2 times 2.5, it doesn't give, is that right? No, that's totally not right. That's 1.6. I'm totally okay with making mistakes. I hope you are too. My willingness to make mistakes is part of what makes me powerful as a mathematician and scientist. So I want you to be willing to make mistakes, to say wrong things. Okay, so 1.6 inches an hour. Okay, but that was across this 2.5 hour window. And I think that that's really important to emphasize, that this is across some long time window. So what's it right now? What's the rate that the snow is falling right now? Okay. Well, this measured across 2.5 hours. So it's like, well, I should go outside every 10 minutes, right? I should go outside once a minute. I should go outside every 30 seconds and look at this thing. I should go outside and look at the yardstick once a second. I should go outside and look at the yardstick every 10th of a second, right? And eventually we're going to reach the resolution of what these devices can measure for us. And we have to accept that snowfall isn't a great analogy for this because there's some real measurement problems for it. But I chose this as an example because it's something that probably most Wisconsin people are familiar with, the depth of snow, and then thinking about how fast the snow is falling. And 1.6 inches an hour it's a very heavy snowstorm. Okay, so what do we want to do if we want to get the most accurate measurement for this thing? What do we want to do? Okay, we want to get the most accurate measurement. I'm not going to measure every 2.5 hours. That's a long time, right? I want to measure across small time windows. I want to measure across the smallest possible time window to give me the most accurate possible reading. So what we're going to do is we're going to take this value right here and we're going to make that thing go to 0. I want to drive that smaller and smaller intervals until eventually it comes up with the number that's absolutely right now. And what that's going to do is it's going to force this number to also go to 0 because, right, as this thing gets smaller and smaller, there's less and less change that happened over that shorter and shorter time period. Okay? So this process of make it go to 0, right here, this process of make it go to 0 to get the most accurate measurement, right? Most accurate measurement of, what are we measuring? The most accurate possible measurement of df dt. That was an atrocious F. For that, I do apologize. Okay. It's the most accurate possible measurement of df dt, assuming infinite resolution on these measurements right here. This process, make it go to 0, is the underpinning of both derivatives and integrals. Okay? So this part right here, make it go to 0, this is limits. It's this theoretical underpinning that drives both derivatives and integrals. It's the theoretical foundation for both df dt as well as the integral of f dt. The integral of f dt. How fast is f changing? df dx. The theoretical foundation is this make it go to 0 kind of thing. And as we saw in the snowfall example, you're going to get your best possible measurement of what's going on right now by taking the smallest possible time window for the state variable that you're measuring, right? The original 2.5 hour example, right? what if, like, it stopped snowing for an hour of that time period, right? And it was, like, snowing even more during those other 2 time periods in which it was snowing, right? And so by having very wide delta t's, it opens you up to all sorts of measurement errors, and you only get your most accurate measurement by measuring over instantaneous intervals, just an instant. We're going to make this be 0 in the limit. And that's why we're going to start this class by talking about limits, because the limit is the theoretical foundation for both the derivative and the integral. Thank you very much, and I wish you the best experience with limits as they lead us to our discussion of derivatives and integrals. Thank you.